This is Mrs. O'Neill for AP Chemistry, Chapter 3, Section 5, Empirical Formulas from Analysis. You should have watched the intro lesson on molecules and elements. These are my notes. So there's an empirical formula versus a molecular formula. The empirical formula doesn't always exist, but it helps us mathematically and experimentally get to the molecular formula that does truly exist. And you should realize or know by now that the empirical and molecular formulas are ratios of each other's as far as the ratio of the atoms that are in that molecule. So that's exactly what I just said. Nice little flow chart as always. He talked about mass spectrometer. Hopefully you understood this a little bit, but we are going to talk about this in more depth when we get to between Chapter 7 and Chapter 8. I do like a Section 7.5, something new that they put into the AP curriculum. And what happens here is you have a sample, it gets reflected, and it comes out with this chart. And this is the chart that actually is the important thing here. Relative abundance, doesn't that sound like isotopes? And here's your masses of those and how much they are. So we're going to talk a little bit more about isotopes and what that really gives us from the mass spectrometer. He also did then some examples of something like vitamin C, and he took the mass of each element that is detected as you put this vitamin C through this machine. So when you put in vitamin C, you get the carbon, the hydrogen, and oxygen, and depending on how much of each, you can figure out what that formula would be. He talked about ratio of masses, right? It would be the same per substance, and gave you another example of gold. So grams to moles using formula mass, we know this now already using the mole in the last section. And again, just to give you a reminder that it's always per 1 mole, it's grams per mole, grams per mole, grams per 1 mole, and it gives you this ratio between the 3 elements. So it helps us find what's called the empirical formula. Now this is kind of goofy, right? He showed you that 1.33, and that's where you might have to actually do some multiplying because that doesn't make any sense, that 1.33. But it gives you just a little bit more detail. So onto your packet notes. In this section, you're going to apply this mole concept in order to determine these chemical formulas from the masses of each of those elements in that compound. So pause the video, fill in the notes, and then play to hear my words. So we want to remember that the empirical formula is the lowest ratio of the atoms in that molecule, and it may not exist. But the molecular formula, on the other hand, is the actual ratio of those atoms that do exist. I actually call this the multiplier. I'm not sure what it's really called or whatever. That's what I call it, the multiplier. We're going to take its molar mass and divide it by the empirical formula mass and get a multiplier that we're going to multiply those subscripts, the ratio of those atoms in that compound. So the game plan for these problems, and I'm not going to go into great detail because most of the time they don't ask you for an actual empirical formula problem, but you still want to remember that there's a concept and that there are conversions and how to get through where we need to get to. So some teachers like to say percent to mass, mass to moles, divide by the smallest and multiply until whole. However you want to remember it, if that helps you, that's great. So you want to take that percent that they give you and that equals the mass. You want to convert that to moles. You're going to divide by the smallest number to get your subscripts. When you get to the molecular formula, then you're going to use that multiplier that I call it and use it to multiply those subscripts in the empirical formula to get the correct subscripts in the molecular formula. So here's an example. So here again, I have percentage of each of those elements, and I gave you the molecular mass. So again, I'm going to go back here. Percent equals grams. So percent to mass, mass to moles, and then divide by that smallest and multiply until whole. So if you want to try to give it a shot, pause the video, see if you can do the problem, and then play to hear my words and answers. So there's part of it, there's the phosphorus part, and there's the oxygen part. If you didn't get that so far, go back and try to rethink what you're doing. Then we look at our mole numbers, and we have to divide by which one's the smallest. So we're going to divide by the 1.82. we're going to get the 1 to 1.5. There's no such thing as 0.5 of an atom. So what do we got to do? Multiply both by 2 to get whole numbers. So our empirical formula is P2O3. Now what are we going to do for the molecular formula? We got to get that multiplier. So we're going to take the molar mass divided by the empirical formula mass. So hopefully your mass here is correct. So here's the molecular mass that they gave us, and the empirical formula comes from the molar mass that you're going to find using the P2O3. So you should get 220 divided by 110 to give you a 2 multiplier. So you're going to take your P2O3 and multiply it by 2. P2O6 is the molecular formula. Again, this compound truly does exist. The other one may or may not. Combustion analysis is just another lab technique to determine empirical formulas of a compound. And here's just a quick example because you never know what you're going to see on the AP exam. So you take a sample and you're going to burn it completely. That's why the H2O is coming in there, so we can burn it completely. And then there's 2 absorbers. So this particular absorber is going to absorb all the H2O molecules, and this absorber is going to absorb all the CO2 molecules. And of course, whatever mass is gained by the absorbers is going to be the mass of that CO2 and the H2O produced. And we'll talk a little bit more about this later. See you in class.